Hello, welcome to my talk at the AI seminar. So, as you guys know, and I guess I should mention this is joint work with Chaba, who just introduced me, and another person named Gellert, who works under Chaba at DeepMind, who was extremely helpful for this. Yeah, so I spent some time thinking about how I should like project or the title for this talk, and somehow I chose this really long thing that many people probably got scared and didn't show up or something for this. So I'm not even going to read it. And then I decided to change the name for this talk, so you guys have just the main idea at the start. And really, this is all you need to know to get started, which is that I'm going to talk about offline RL, and I'm going to try to claim that offline RL needs less data if you have trajectories as your data. And then there's going to be like some assumptions and all these caveats and other things. But this is like the main idea that you should take away from what I'm going to talk about today. Okay. And I'm going to start right away with pointing this, is that as Chaba mentioned, I work in RL theory. And this doesn't always have to be the case, but it is the case here, which is that this is a purely theoretical talk and a purely theoretical result. So for the case of this one, there is no experiment. So just warning everyone, it's going to be all math, but hopefully, and this is my goal, hopefully I've made it like digestible for everyone, even people outside of RL theory, and you guys can get like an idea of what we do in this RL theory world at like a simplified level. Okay. But as any good RL theorist should do, is they have to motivate their work, especially when they submit their papers. So I had to always throw in this motivation slide of somehow justifying why this is an important question. And I actually do think it is an important question. But anyways, the things that came to mind originally was this idea, like a lot of things have safety concerns. So you don't want to be gathering data online. You maybe like, and there's a lot of offline data. So you can use that to first kind of like decide on how you should act or what you should do in this world. And like there's examples of things that have used a lot of offline data like ChatGPT, right? So there's a lot of offline. It would be kind of interesting to ask what it thinks is a good motivation for using offline data and reinforcement learning. And it seemed to agree with my original first claim, which is, you can do like safe use cases, and when there's risks of gathering data online and doing the wrong things and taking the wrong actions, and so on. Okay, so hopefully this is like some motivation about why offline RL or offline data is a useful setting. Okay, now we start the talk. So this is what the talk's going to look like. I'm going to spend quite a lot of time on the first two parts. So I'm going to start with introducing the problem. And this is just going to be a lot of details about RL and what offline RL is. Then I'm going to spend almost the entire talk explaining about what we knew in offline RL. And I think this is really important to like set the stage of exactly what we did. Because if you don't know what's the problem, what's been done before, you have no idea like what this means or where this stands. Then I'm going to present a result, which is going to be super short, because like if you know everything that happened before and then I present to you the problem, you should just be like, okay, did you solve it or not? And talk a little bit about how we do it at like a very high level. And yeah, and then I talk about what's next. But just so you guys know. And this is going to be kind of like a very gradual buildup. The trajectory part and everything and our work is really coming near the end. So just like bear with me with the story. Yeah. Okay, so we start with the problem. Oh, and feel free to like ask questions throughout. It should be pretty interactive if you want. Okay, we start very simple. So we have, well, I mean, for people in RL, I guess it's simple. If not, I have all the details, I hope, here. So we're working with MDPs, as we usually do in RL. And here we're going to be working with these finite horizon MDPs. And all that means is that, well, we'll come to the finite part in a second. But so we're going to have the state space. And this is without loss of generality. Basically, we're going to have a state space that has this like layered structure. So there's going to be these stages. That's the horizon part. And in each stage, there's going to be a state space for that stage. Okay. And you can ask questions if you want about this, but this is without loss of generality, basically. The second thing is A is the action space, and we're going to assume it's finite for the talk. And then P is the transition function. So this is like if you're at some state and you're at some action, this is the probability of going to some next state, or it's the distribution of that. Then R is the reward function. And for the talk, we're also going to just assume this is deterministic, but it doesn't need to be. And then here, H is the finite horizon part, which is the horizon of the MDP. This means that when the agent interacts with the MDP, it interacts for H steps, and then the interaction ends, and then it restarts. Other places they call like episodic, but the episode has like a fixed end time. So I'm going to give some examples next. So like, oh, and then there's a start state. So this is where you start. A quick example that almost fits this is tic-tac-toe. So here you like have the start state of tic-tac-toe. There's no X's or O's on it. Then you play the game for 9 moves, and then the game ends. You could end a little bit early, but you could imagine like taking actions that mean nothing after. Something like this. And then the actions are like where your X or your O or something like this. But there's like a finite horizon where it ends. Simple case. I'm going to give another example, which is like the classic drawing out of an MDP. And this one, you're going to see this picture a lot throughout the talk. So get familiar with it, I guess, is the point. I'm going to keep using this to refer to a lot of the other assumptions and things that happen throughout the talk. Okay, so there's states. These are the squares. And then there's actions, which are the lines. Each line represents an action. And so here, and this is not obvious from the picture, but the horizon is 3. And what this would mean is that like you take one step, you get to here. The second step, you can get somewhere to here. And then in the third step, you end up in the same state and it terminates here. Okay, so it terminates at that point. You could imagine it could keep going if you wanted, but here we're just assuming the horizon is 3. Okay, the action set is A1 and A2, so there's 2 actions. And this is like to showcase what the state space layering thing looks like. So the whole state space is the union of all the states you see, but the states at each stage are the states that are reachable at that stage. So like at stage 1, you can be in state 1. In stage 2, you can be at state 2 or you can be at S2 or S2 prime, and at stage 3, you could be at S3. And the rewards would look something like this, right? The rewards are a function saying, if you're at some state and you take an action, how much reward do you get? So they're just functions that take as input states and actions and output the reward. This is just some arbitrary reward, but I'm going to keep it throughout the talk because it's going to be actually useful, specifically this reward structure. And then finally, the transitions look something like this, right? So like if you're at S1, the probability you go to S2 is 1. And on the contrary, if you took A2, the probability you end up in S2 is 0, because with probability 1, you end up at S2 prime. Okay. Hopefully that's pretty straightforward. Okay. So that's our environment, the MDP. The other thing that the thing that interacts with the environment is going to be an agent. And we're going to describe the agent as something called a policy. Okay, so like agent, policy, same thing. And here, a policy, or the agent, is just a map from states to distributions over actions, right? So if the distribution was like deterministic or like fixed at one action, you could think of the policy as just like, if you're at one state, what action do you take? And this basically tells you how the agent is going to behave everywhere in the environment. Okay. And then there's usually this picture, and this is for the online RL setting. So we're going to change it slightly for the offline one, but this is what it usually looks like for the online one, which is you have this agent and this MDP, and the agent starts at some state S1, it takes an action, and then the MDP returns the corresponding reward in next state from that action. And then it keeps interacting in this loop. Okay. But in the offline setting, the things that change is we no longer have access to interacting with this MDP. Okay. So instead, we're going to have something called offline data, or like offline interactions with the MDP. And it's going to look in this form. Okay. And I'm going to show an example of what this looks like, and let me just quickly mention. So the things to note here is these look like interactions with the MDP. So like you have like, for instance, if you just look at this one, it's like you were at some state, an action was taken, this is the reward you received, and this is the next state you got to, okay? And here, the superscripts are going to be data indices. So you can see here, this is the first like data. This is there's going to be more data, and there's n of these tuples of data. And the subscripts are stages. So this would be like the data you got from stage 1. This is the data you got from stage H. And this is like the first data index. So once again, you can think of having n of these tuples, where each tuple contains one interaction. Okay, I'll show a picture of MDP in a second. And once again, the R is just you sample the reward you got from that state in action, and the S bar is the next state. And maybe the important thing to note, which is maybe confusing with all these subscripts and superscripts and stuff, is that the S bars are not equal to the S, not necessarily going to be equal to the not S bars. So this means like the state you transition to here is not equal to the state you started at the next stage. Okay. And I'll show that very clearly in this next diagram, hopefully. Okay, so we go back to this MDP. And I'm just gonna, so one thing is instead of having this complicated R's everywhere, I'm just gonna simplify them to like R equals 0, which means this is the reward you got. So just to remove some clutter. Okay, and so now this is what data might look like. So if you had any one, so that means you had one like tuple of offline data, right? It would look something like this. So here the horizon was 3, if you recall. So what that means is we have one data point for each step in the horizon. So for each stage. And it would look something like this. So here you have, you're like, for instance, this one is you were at S1, you took action A1, you got the reward, and you went to S2. In this one, you were at S2 prime, and then so on, you went to S3. Okay, so hopefully that part makes sense. And then the critical thing to note is here, there was no assumption, right, that these data points between stages had, like this S2 did not equal to S2 prime, okay? If it was equal, this would be called something trajectory data, which I'm like implying and so on, but this is like the important thing to note. So this is, we're not dealing with trajectory data yet. We're dealing with this just general offline data. And here, this is, these two are not equal for the purpose of this talk. And yeah, okay. Hopefully that makes sense. So moving on. So what is our problem? Like the goal of the, yeah, what's the problem here? So to define the problem, I'm going to need to find two more things, and they're going to be these value functions. And so to understand this value function, we call this like a v pi of s. To understand this, you think of it like this. If you started at s and you followed policy pi, in expectation, how much reward would you accumulate from that state till the end of the interaction? Okay, and then here you can just see that as it's the sum of the rewards, condition that you started at sh, if you were to follow policy pi, and this is an expectation, the amount of reward you would get. Because there's like randomness in the transitions and potentially in the rewards and stuff like this. And similarly, we have a thing like a thing called an action value function, which is the amount of value you get if you started in state sh and took action ah. Okay. Turns out these quantities are useful throughout the talk and for defining the problem. And there's one more quantity we should know, which is the best, kind of the optimal policy. And this is just the policy that gives you the most value. So it's the policy that gathers the most expected reward from the beginning, the start state S1. Okay. That should hopefully be intuitive. And so here's the problem statement. This is like what a theoretical RL problem statement would look like. And this is a common way of formulating it, which is that for any epsilon, and epsilon is going to be like your accuracy of your resulting policy, with access to offline data of size n, which is a polynomial of all these quantities you care about, your goal is to find a policy that is close to pi star. Okay, so before we look at this math maybe a little more closely, in other words, it's really just asking, can you find a good policy? And good means here epsilon close to like the best possible with a small amount of offline data. And here small amount just means that n is a polynomial. It's not like exponential in any of these quantities. Okay. Is there any questions about the objective? Yeah, so just to repeat for people online. So the question was like the states, actions, the probabilities, and rewards are known ahead of time. So the answer is no. So you know, like you don't, okay, we can assume but you can assume that it knows the states and actions, but it certainly does not know the transition probabilities and the rewards. So if you knew that, then you could just like solve this classic dynamic programming problem. So instead, that's the difficulty. You don't know the transitions and you don't know the reward function, but you have data from them. And so from this, you're trying to understand the environment and then learn how to act on it. So P and R are unknown. That's simple. Yeah. Yeah. So yeah, so far this you would call a taboo. So we've done no function approximation or anything yet. It's going to come up. And the question was, is this just a tabular setting? Okay. So we move on. This is like the beginning of all of RL kind of, this is the problem. And then we're going to tack on other assumptions, and we say like why you would try to assume this, hopefully. Okay, so here's the problem. And this is usually called offline RL because you have offline data. Okay. So yeah, I guess this next slide already starts addressing this, which is like some people are okay with working with having basically this like dependence on the state space and stuff. But it turns out that in a lot of problems, the state space is really large. And just like for some examples, like chess has a really large state space, robotics has a really large state space. So there's a lot of problems that have really large state spaces. So it'd be nice if we did not depend on the state space. So if we go back to the problem, what that means is if we look here, this cardinality of the state space, we don't want that in the dependence on how much data we need. Okay, because if the state space is like enormous, like 10 to the 40, you're going to need 10 to the 40 offline data samples. That's not good. So we just say, okay, like here's our new objective, remove the S part. Can we do this? Okay, so that's the new problem. And so the way I like viewing all of this RL theory stuff, and this is how the rest of the presentation is basically going to go, is that there is this space of assumptions, and you really start with no assumptions. You want to see, can you solve the problem with no further assumptions on the problem? And you can think about two assumptions, like making assumptions on two parts of the problem, which is you can assume things on the quality of data you have. So this is like the offline data of size. And you can assume like, how good is that data? Like, does it represent all the MDP well? Does it cover things, whatever, things like this? You can make assumptions on that. Ideally, you make no assumptions. And the other thing, you can make assumptions on the MDP, which means like, how does the MDP look like? Does the transitions follow some certain structure? Are the values between some range? Things like this. So ideally, the goal is to just like solve this and all types of data. This would be like the holy grail, right? You'd really want this. And so then people in theory world are like, okay, let's see, can we do this, right? So we'll see this table throughout, and we're going to keep adding things to it, which is that you start with all possible data and all possible MDPs, and you ask, can you solve the problem? Unsurprisingly, okay, so this is the problem. This is where you really start in our theory. So then now starts the related work, which is we're going to build up our understanding of what's possible and what assumptions we need to add and when. Okay, so here we go. So unsurprisingly, the answer to this question is no. You can't just solve all your MDPs and have data that can scale with the state space and its polynomial and everything else. And you can see this super easily, just because the data, if the data is really bad, then you really can't do anything. And this is like a super simple example, which is that imagine there's one really important state, action, and reward and next state in the MDP. So the way to think about this is like, imagine the reward is 0 everywhere, except at one specific state. If your offline data doesn't have that specific state, then you can't do anything. You can't learn that there's a reward of 1 there. And so then it's impossible to learn a good policy unless you have people from that state. So you need to depend on the state space on how much data you have, right? If you have like a sample from every single state in your state space, then you would see this, but otherwise you can't do this. So yeah, so that quickly ruins our kind of big plan here. So at this, as a theorist, you say, okay, like, let me solve this by assuming that the data is actually good, whatever good means. And we're going to make an assumption here on that, which is that the term in theory world is called concentrability. But really, all this means is you have good coverage of the state and action space. And this is like directly addressing this kind of problem, right? Okay. So what that means is that if we just return back to this data thing, we're going to just add a little bit more structure to how the data was gathered, which is we're going to assume that these states and actions that you're getting the rewards and next states from come from some distribution, which I'm going to call the data gathering distribution. It's this mu thing. That's all. Nothing new there. So if you go back to this picture, all that means is that like when you look at this data, these S1 and A1s and S2 prime, they came from some distribution. The reason I do this is because then we can state the assumption like formally, which is that this concentrability assumption, okay, it says there's some equations. All I really want to communicate from this thing is that, maybe I should say this first, which is that this data gathering distribution, which is gathering your SA pairs, is gathering data as well as any possible policy in the MDP. Okay, so what that means is like, if you run any policy in the MDP, whatever states and action it visits, which is this numerator here, my data gathering distribution is pretty close, meaning the ratio doesn't become very large. Okay, so it means I have like some samples from basically every state and action that any policy can visit. Okay, So we make this assumption, and then we return to the problem and we say, okay, so our problem is no longer to do this way. We need to, it's not just any offline data. We have offline data that satisfies concentrability. And so in other words, this is find a good policy with a small amount of offline data that has good coverage. Okay. And so we go back to this table and we have this question mark here. Can you do things with concentrability? And the question should be maybe not so surprising. And the question is no, or sorry, the answer is no to this question. And there is a theorem that states why this is not the case. I'm not going to go over the details of how it shows it. But the important thing is that the way, like what it states is that you can't do this once again unless the number of samples depends on your state space size. And this should still probably not be so surprising because like you'd still need to see this like hard example. Okay. So we go back here and then we have, we need to somehow address this problem, right? So we have this number of states that's a problem in the dependence. So one way to do this, and this is like a classic way to do this, is to enforce some structure on how things look over the state space. So like probably nearby state, okay, in some problems, right? And this is not all MDP, but in some MDPs, nearby states will have similar like structure and reward maybe, and how much value you get from them. So this is usually summarized by something in theory world called linearly qpi-realizable. In other empirical RL stuff, or like in theory world too, it's called like you assume you can function. So this means you compress the values, or said otherwise, like similar states will have similar values. In this way, you only learn the value for some states, and that gives you a representation of the value of all the states around. So this kind of like should intuitively give you some hope that you can address this problem, that you no longer need to visit all the states. You can just see some representative states, and then they give you some information about all the states nearby. And yeah, so we add to the table, and we ask, can we solve the problem here? So the first one is, once again, if you don't have any assumptions on the data, you still can't do anything because you still have the same similar problem. But now, if you have assumptions that you have good data coverage, which is this concentrability, and you've assumed you can like similar states of similar values, what can you do? Okay, and I'm just going to formalize the qpi realizability thing just super briefly here, which is here and it's linear representation. So we're going to assume we can approximate values with linear functions. And so what this looks like is you first start with a feature map, and you should think of a feature map as first of all being given to the agent. Okay, and an example of a feature map would mean like things that explain the problem pretty simply with a small number of dimensions. So like an example is, if you have a pixel image of like a self-driving car, you can think of different things such as like the number of pedestrians, a number representing that, and the number of other cars you see in the photo, and like the distance to stop sign or something like this, as being just numbers in a vector, and this would be called like your feature. Okay, so once again, you take an image, a complicated thing, super high dimensional, and then you map that to just like a small vector that represents useful things about the problem, hence the word feature. So it's like the feature of the image. Okay. And so then this is what the assumption looks like, this linear qpi realizability. And yeah, all you really need to see from this is it's just saying that this qpi function, which is the value function, can be written as a linear function. And it can be written as a linear function in the features phi. Okay. And why, like, how does this map to being only needing to know a small number of states and whatever? It maps to that because if you could learn what these parameters theta are, right, then you would know qpi. And now you don't need to represent qpi as a giant table that depends on the number of states and actions. You can just represent it by this series of vectors theta pi to theta pi h, so one for each stage. That's only d-dimensional. And here you hope d is much smaller, right? So like in this pixel image thing, it might be like if we just use number of pedestrians, number of other cars, and distance to stop sign, you'd have d is equal to 3. Okay. So this is the hope. This is the, and maybe to give some motivation of why use this assumption and stuff is because it's being used in the online RL setting, right? So the online RL setting, you choose how you gather the data. And it turns out that this was in 2023, it turns out that if you do this in online RL, things work with this assumption. So you can interact with the MDP, that's what online RL means. And here, by things work, it means you get the result we were hoping for with no dependence on S. Okay, so this should give us some hope in the offline problem, hopefully. And then so we return to the offline problem. We add this extra thing, which is now we have linear qpi realizability and access to offline data that is good coverage. And we ask, what can we solve this, can we solve this problem? And here now we add this dependence on D, which we're okay with depending on. Yeah, so you really do assume that the agent is given this feature function beforehand. That satisfies this. I'm not telling you at all how you got this. It just so happens you end up having this beautiful feature function. And we can talk about where you can actually get this in the real world or whatever. But yeah, it's we're assuming, as any good theorist would, you make some assumptions. So there's so we assume we're given this feature function that satisfies these properties. And then we ask, like, even if you had this feature function, can you do something, right? Like, if you can do something, okay, then we can think about where we get these feature functions and so on and so on. But turns out the answer is actually no. So even if you had this good feature function and you could represent these value functions linearly, and you had this coverage of the data in this way I described, it turns out you still didn't achieve our objective. Okay. And so at this point, we're like almost at the forming the problem. At this point, you have two choices, right? Which is like, do you make more assumptions on the MDP, or do you make more assumptions on the data? Okay. And maybe like foreshadowing what's going to happen, we're going to make more assumptions on the data. But before I do that, I'm just going to mention that there is other work, and this will be useful to understand our work actually, that makes more assumptions on the MDP. Oh, this was just a negative result. Okay. So, and this, they call it linear MDP. And what this means is that you don't assume value functions are, like, you don't do function approximation on value functions, but you do function approximation on the actual MDP itself. So you assume transitions and rewards can be approximated, and specifically approximated as linear functions of similar style features and stuff. Okay, this turns out to be a stronger assumption than the other one. So maybe one other thing to mention, when I draw these like circles being contained in the other, it means that all linear MDPs are linearly Q-pi realizable, but not all linearly Q-pi realizable are like linear. So this is a smaller set of MDPs that satisfy this. So we're constantly basically saying we're working with a smaller and smaller set of MDPs that satisfy these properties, and only for those do we have guarantees. Okay, so like at some point you can imagine you make so many assumptions that there's absolutely no MDPs that you say, oh, for those you could work, but like you should really check that there is any MDPs that satisfy this. It turns out there is some that will satisfy this, and it's not like a tiny amount, I guess. Okay, so that's the assumption, and I'm just gonna, so then you add this column to the table and you ask, okay, what can you do for linear MDPs? And once again, if you have no assumptions on the data, it turns out you still can't do anything. But okay, we'll answer this in a second. Here's the assumption formally. All you need to really see is that just like for the value functions, it's linear in these features phi, right? So instead of having values represented linearly, you're now representing rewards in transitions. So return to this table, and the answer turns out to be yes. So this is some other work from actually way longer than 2019, but this is, anyways. Point is, this was known that if you had linear MDPs, you could do something like this. And yeah, okay, so do this. So then the question is, like, without assuming linear MDPs, can you assume something like, what's the kind of like the minimal assumption you could do on the data that will also give you a positive result? Okay, and so then that goes to our work. So we, like, instead of assuming the linear MDP thing, we're going to instead still stick with the linear Q-pi realizable stuff, and we're going to assume something stronger than concentrability, right? So you need something more than general coverage. And it turns out that if you do, well, here's the assumption. It's called concentrability, and you've assumed that the data is also looks like trajectories, and I'll go over what trajectories means formally in a second here. So if you assume this, then we ask the question, like, what can you do? Okay, and so it turns out if you have no assumptions on function approximation at all, unsurprisingly, you can't do anything because you still need to see all the states. If you have a linear MDP, this is a stronger data assumption. So obviously, the thing that worked for the weaker data assumption, it still works. So here is the table, the cell of the table we aim to fill in with, like, what is the result here, right? So this would be, you need weaker assumptions on the MDP structure, but you make stronger assumptions on the data. Okay, and once again, this is like trying to like build the picture of what are the minimal assumptions on data and MDP space such that things work theoretically. Okay, so then again, kind of this is how basically all of theory work could be framed. It's like every time someone makes assumptions, it's for the most part for like good reasons of like trying to find what is this minimum structure that's needed to get something positive. Okay. So now I'm going to describe what trajectory data is a little bit more formally. So first claim is there's some this assumption, which is that you can imagine there is some cases where it's natural to gather data in trajectories. So for instance, a person driving like a car, which would be like the policy, from point A to point B, you would call that a trajectory if you had all the data from like the start point of driving till the end point of driving. That's what it means to have trajectory data. So it's not like a very unnatural way to gather data, is just all I'm trying to argue here. Okay, after that being said, here is what it looks like. So the assumption is just that the offline data consists of trajectories. And what are these trajectories? So you have n trajectories. And what are each of these trajectories look like? What they look like is almost the same as what you saw before, except there's this special property that basically it's this S2, which I haven't, well, you'll see it in a second. So these trajectories are gathered by a policy, which means that you get state, action, reward, next state, action, reward, and so on. And the way you gather this is through a policy interacting with the MDP. So this is just described here that like the actions are gathered through some policy, and this policy pi g I'm going to call the data gathering policy. Okay, and just to like map this to the previous way you saw data, it would look something like this. So if we wrote it in this structure, which is like S A R S bar, basically the assumption is that S bar equals to the S of the next stage. So these two things are equal. And it should be made much more clear when you look at a picture of the MDP. So when we look at this MDP, you saw here that for the first stage, you had this type of data. And then for the next stage, you had S2 prime starting from some state that is not the same state as the last stage ended up in. So naturally, the trajectory thing just means there's like, from start to finish, they're all connected. So what you would do, trajectory data would look like this. Basically, you replace this S2 prime with S2 here. So importantly, S2 equals S2 prime, or like the green and orange ones match. That's all it means. So you have this like connection across your data. Okay. And that's the trajectory data. And then you remember there was this concentrability thing, which said that like, oh, your data actually covers all states and actions well. There was this mu distribution. Now this mu distribution is just this other quantity, but all this quantity is saying is that your data gathering policy, which is pi g, which gathers for you, gathers data just as well as any other policy. Okay, so this pi g basically visits every action as likely as any policy could visit any state in action. Okay, up to some constant factor c. And you can imagine, yeah. Okay, so that's what that is. So that definitely restricts like the type of data that you can get. Okay, so the problem now becomes you add this extra assumption, which is now you have offline trajectory data that satisfies concentrability, and you still have the linear q pi, and yeah, okay. So we go back to this table, and so now this is like we built up this whole story of the related work, and this is basically where our project began, which is like there's this landscape, and we wanted to answer this question. And so now we move on to what we know now. And I guess I kind of gave it away with the title, which is that here's the answer, is that we found that you can do this. So if you end up with trajectory data, you actually end up with a positive result here. Okay. So yes, and maybe just to really drive things home here. So it becomes positive, and it's in the setting of, so you have this trajectory data that has good coverage. That's the concentrability part. And importantly, it's for the larger set of MDPs, which are the linearly q pi realizable MDPs, right? Which is a larger set of MDPs than linear MDPs. And there is actually examples, okay, like this is not just like you can actually construct an MDP which is linearly q pi realizable, which means its values are linear, but its transitions and rewards are not. And we're going to actually, like, that's going to be part of understanding how this works. Okay, I think it's to finish things, which is okay, actually quite fun. Okay, so that's really the main takeaway of this whole story. And all that's going to happen next is explaining how this is achieved at a very high level. Yeah, they have to be all from the same pi. And so the question was, do all the trajectories have to be from the same data gathering policy pi g? And the answer is, for this result, they do all have to be from the same policy. Yeah, there's some consideration to making it like some mixture of policies, like you had some mixture of policies, but then you have some difficulties with what the linear, like in the linear, okay. Basically, if you have this mixture, what ends up happening is that your policies don't become these memoryless policies. They don't become policies that only depend on the current state to take actions. And we have this value function approximation assumption, this linear QPy realizable assumption that only holds for policies that are these memoryless policies. But there's maybe some hope of like still making, but yeah, it's like kind of a technical thing, but okay. There was some thought about this though, whether it just naturally extends this or not, and it's not obvious. Okay, but it's a good question because like you probably don't have data from just like the same policy over and over. Like for instance, the car driving thing, you probably have different people, right, gathering data. So that could be like different policies. So this is what the result looks like as like a statement. This is almost exactly what it is in the paper, which is that, and maybe we can go over this just to like be very formal. So it says something like this, which is like for any epsilon is your accuracy level with these assumptions of linear QPy realizability, access to offline trajectory data that satisfies this good coverage called concentrability, and that offline data is of size only polynomial in the quantities you care about, which does not contain the size of the state space, then our algorithm is going to output a policy pi that is as close as pi star, which is the optimal one, from in value. So it's going to output a policy pi that's as close to the optimal one in value from the start state up to an accuracy of epsilon. That's what like yeah. Okay, so next, all that's left is to go over how this is kind of achieved, and let's go ahead with that. So in order to understand how this is achieved, we should go back to some related work I mentioned before, which is that in the setting of linear QPy realizability, and so that and then you look at the online setting. So here, there's no assumptions on how data is gathered because you gather it yourself in the online setting. I mentioned that there was this result that in 2023 showed that things work in this setting, right? So you can kind of see like, okay, in the online one, you get to pick how your data is gathered. So you can gather it in like a good systematic way that covers things you care about. And they have the same assumption on MDPs, which is linear QPy realizability. So it's like, okay, like what's going on? Clearly, there's just some like mismatch in how what we assume that our data is in the offline setting and how they're gathering data. So this gave some motivation, like how did things like how did their algorithm work? And the way their algorithm worked is at a high level. This is like the roughly how things work. Is they made this is the big observation they made, which is that if you can modify these MDPs that are linearly QPy reliable, linear MDPs. So you can make a modification to the MDP and without too much loss, maybe I should have put approximately, they approximately become linear MDPs, which means linear in value functions mean transitions and rewards are approximately linear if you modify the MDP in some way. And so the algorithm roughly MDP, and then just run an algorithm that works in linear MDPs because we know in linear MDPs things work. Okay, so this was the online setting. So now you can look at the offline setting and be like, okay, we saw, okay, well, I guess I highlight things here. So we can do this part clearly in the offline setting, like things work in the linear MDP stuff. And we saw that things don't work in the linear QPy setting. So clearly there's some like mismatch in this offline thing, which means that it seems that we can't do the step of modifying from linear QPy to linear MDP efficiently in the offline setting. And so we want, but then like, we're like, okay, like in the online thing, clearly like things work. So the question becomes, when can you modify a linear QPy MDP to be a linear MDP, like efficiently? And if we look at the online thing, it turns out that, well, the answer turns out to be when you have trajectory data, as we I guess, as I've been mentioning. But like the intuition is if you look at the online interactions look like you're gathering trajectories. You have a full interaction with the MDP from start to finish. And the data there really does look like trajectories. Okay, so that was like the observation. So unsurprisingly, our algorithm is the exact same algorithm roughly. And it's modify this linear QPy MDP to be like linearly QPy realizable MDP to be a linear MDP, and then run the algorithm that works for linear MDPs. So that's what it kind of looks like. So I guess the disclaimer is that the algorithm isn't actually just this simple, but this is like the kind of the intuition behind it. It does turn out to be a bit longer of a story than just this, but this is like the intuition. So maybe I try to make it like the story sound very simple, but hopefully it doesn't make the work sound almost obvious. But yeah, So it did turn out to be harder than just like a couple lines of just changing things. Well, this is the main story. Okay. So all that's really left to discuss is just like, how do you do these two steps? And I think I can do this super quickly without going over some silly, okay. So the first thing, let's just go over the first step of the algorithm and then we can go over the other one. And so I'm just gonna explain why modifying an MDP that has linear value functions could potentially create an MDP that then has linear transitions and rewards. Okay. So the story is something like this. We go back to our same MDP. And first of all, we need to like the assumption we start with is that value functions are linearly representable. So what that would mean is that first of all, we should look at what the value functions look like. The value functions are super simple in this MDP. From here, the value is just 1 for all policies. And if you go to any action, so it's super easy. Here, the value is 1 for the top and 0.5 for the bottom, but it doesn't matter what action you take. And then here, the value is 0. So that's all I'm saying here. Then all I need to do is just give you a set of features and a parameter that can make these value functions look like linear functions. So it turns out that the features and parameters, there exists some. This is what QPy realizability would look like. I just give you some features that satisfy this property, that this parameter theta times features gives you these value functions. It turns out that you can do this super simply. Like it's a one-dimensional feature vector and it's a one-dimensional parameter theta. You can check, but it's not that important to check right now. Like the point is it satisfies it. But it turns out that this is not a linear MDP. And this should be super obvious why this can be the case, because here you can see that the features are one-dimensional, which means that from this state, no matter the action you take, it gives you the same number here. Okay, this didn't need to be the case, but it turns out that like in this case, since the value for both actions A1 and A2 is the same, you can use the same feature for both actions. So that's reflected here, that phi of S1 for no matter the action is the exact same number. But the reward is different. Okay, so all I'm trying to say is that if you have some state and all the different actions have the same value, then you can just represent the value in a very, very simple way. But what might happen is you might lose information that the rewards are different from that state, or that the transitions are different. Okay. All this is saying is that if you have a QPy realizable MDP, meaning values can be approximated, it does not mean the rewards and the transitions can be approximated. And so here's the trick of how you modify this. It turns out that the issue is exactly these states that have the same Q value for all the policies and all the actions. So this is exactly these like states are causing the problems. Because if you have a state where the values all look the same, then it really doesn't matter what action you take. But it might be that the rewards and transitions are different. So here's the modification. The modification is as simple as remove all these states, except for the start and end state, because you still need to maintain the structure of the MDP, that have the same value functions under all policies and under all actions. And it actually, in the actual thing, it's like remove things that are approximately, but like for the purposes of this. And that would look like removing these two states in the middle, because for all the actions, they have the same values. And so if you do this modification, you end up with an MDP that has linear rewards and linear transitions. And that would look like this. So I gave it like a very obviously simple example to showcase this, but this turns out to be the modification you need to do. And this is the observation that the online RL work had. Okay. And so then all that happens is then what algorithm do you run? And you run something like an approximate value iteration algorithm. And this turns out to work. Okay, that's the whole story I have for how things work, or how we know this. And so all that's left is describing what's happening next. What did I lie to you guys about or hide and sweep under the rug? Okay, so here's the future work, which is really what's next. So you might have noticed that we only require the size of the offline data set to be a polynomial here. But we didn't talk about anything about the computation. So we said like, oh, all we care about is how much data you need. We never talked about like how long it takes to compute. So turns out the algorithm is actually this like really ugly optimization problem, something like approximate value iteration, and it's not computationally efficient, and you can't run it in polynomial time of these quantities. So the one open problem is, can this problem be solved computationally efficiently? So we only showed sample efficiency, and I don't know if the whole thing is always talking about how much data you need. I never talked about actually running an algorithm. So slightly why there was no experiments as well, because like it's not an algorithm you probably want to run. Second thing is, you might have noticed that I kept mentioning that like small amount of data is a polynomial in some quantities. but I never actually mentioned what the polynomial is. So the polynomial ends up having like, it ends up being this. It ends up being like, you need at least this much data. And so we don't know if this is actually the best possible. And I mean, I don't know if it can, like, it's actually not that bad, but there could possibly be some improvements on specific, yeah, there could be some improvements. But the epsilon is at least optimal. Like this is actually optimal for epsilon in terms of like the number of samples you'd need. Okay. So I think that wraps up everything. So yeah, thank you.